Hello, everyone, and welcome to Chapter 5, Stereoisomerism. What we're going to do today is give our brief introduction to Chapter 5. We're going to define a few types of stereoisomers. I may jump around in terms of a little bit of the chapter. We'll see that I'm just going to bring up a definition from Section 5 up into Section 3. Just so that we can start comparing the different types of stereoisomers that we have in this chapter. So isomers are, by definition, different compounds that have the same molecular formula. And so there are two general types of isomers under this category. And so the first one we've seen before is the idea of the constitutional isomer. Now remember, the constitutional isomer was one that had the same molecular formula, but different connectivity. Those are really important when we talked about naming, right? They had totally different names because there was a different parent chain, a different branch, a different substituent, things like that. Constitutional isomers are completely different from each other, do not have the same physical or chemical properties at all. The other type of isomer that we're going to see in this section is a stereoisomer. Now, a stereoisomer is the same molecular formula, the same connectivity, just different spatial arrangements of atoms. I'm going to call that different orientations. I'm definitely going to make sure we think about this in terms of the same connectivity, though. And the reason for that is because a stereoisomer sometimes could have very similar physical properties, only a few of them. There's going to be a couple of classes of stereoisomers that we're going to see throughout today's lecture and throughout this chapter. And their connectivity will always be the same. We'll have the same exact carbons connected to each other and the same exact oxygens or chlorines or whatever, but they're maybe going to have a different orientation. The first class that we're going to see in just this overview is that idea of cis versus trans. When we saw this back in chapter 4, what we want to be able to say is that when we have a ring system, I'm going to draw this in its skeletal structure with a little perspective formula. These methyls are on the same side. So when we look at that, that pair of methyls, both wedged or both dashed, remember this is a meso compound, but whether they're both wedged or both dashed, that is what we called the cis conformation, the cis formula. And we added that to the name, right? This was cis 1,2-dimethyl cyclohexane. Now on the other side, trans occurs when the substituents are on opposite sides. This is not a meso compound because we could see these are different. We're going to talk about what a meso compound means a little bit later. So right now, just be able to look at these Hayward projections and compare them to the perspective formulas and be able to identify cis versus trans. That's all we really need. So in order to give these compounds that unique IUPAC name, we use the prefixes cis and trans. Now the same is going to be able to be used for a carbon-carbon double bond. The reason for that is because remember, this pi bond cannot rotate. There is a parallel overlap. And if there was any sort of rotation around that carbon-carbon bond, the parallel relationship would break, and therefore we cannot do that for a carbon-carbon double bond. Pi bonds do not freely rotate, and so therefore double and triple bonds do not freely rotate. With a carbon-carbon double bond, we could have a stereoisomer form, whether their groups are on the same side. Notice the H's are on the same side of this plane. Let's just draw a little bit of a plane right here through the carbon-carbon double bond. And we can label this as top and bottom. We could say left and right, depending on where our carbon-carbon double bond is in the plane with respect to our paper. But notice how those methyl groups are on the same side of the pi bond, and the hydrogens are on the same side of the pi bond. Same thing over on this side. We'll draw that plane of symmetry, and notice how the methyl groups are on opposite sides. The hydrogens are on opposite sides. There's trans for you. So cis and trans, just like before, same versus opposite. Now, this only works for carbon-carbon double bonds if you have a hydrogen on each side. You have to have a hydrogen attached to each carbon of the carbon-carbon double bond. We'll see some examples a little bit later at the end of this chapter where cis and trans for a carbon-carbon double bond is a common naming system, and it is not appropriate for all carbon-carbon double bonds. And we'll get more specific when we get there. Let's go ahead and just practice one more. I just want you to be able to see that even though we're in a skeletal structure, we could have this molecule has a carbon-carbon double bond. So what I would highly recommend is you draw a plane of symmetry or just a line going through that carbon-carbon double bond and identify, does it have a hydrogen on each side? Yes, it does. Let's fill those in on the skeletal structure. Are they on the same side or are they on opposite sides? They're on opposite sides. We're going to practice a lot more in class. However, this is a good first representation that when we start to dissect a molecule and really understand what it looks like, what this will be able to tell us is a lot about the reactivity of the molecule. We'll be able to name it a little bit better, and we'll see some things later on in later chapters, what we can do with cis and trans. Okay. Well, cis and trans isomerism is only one type of the stereometric relationships. There is another one that I don't want to say is more important, but it's more frequent, and that one is called identifying chirality or a chiral molecule. Now, let's go back into history. To really understand this definition that a chiral object is asymmetric, which means that it's not the same as its mirror image. What we're looking at is when a molecule is chiral, we have a specific definition for it. But I really want to go into a little bit about the history as well as we start to look at chirality. Chirality most often results when a carbon atom is bonded to 4 unique groups of atoms. Doesn't mean 4 unique atoms, right? It could be all carbons that is attached to that carbon. However, but what we really need to define is that if the carbon atom is bonded to 4 groups, that carbon is sp3 hybridized. And unique groups, they could be methyls, they could be ethyls, they could be propyls, they could be isopropyls. Those are all different groups. And so you'll see here the most simplistic model. And I want to really point out this one first. The red sphere, the blue sphere, the green sphere, and the white sphere. Let's just get some numbers. 1, 2, 3, 4 different colors, 4 different groups. And what we can start to see here is that those 4 different groups can be arranged in one of 2 ways, in which that they result in a mirror image of each other. Chirality is really, really important in molecules. We'll see a couple of examples later, but when we have 2 molecules that are mirror images of each other, they may have some identical properties, but they are not fully identical. So they may have the same boiling point, they may have the same melting point, they may have the same solubility in water, but they are actually not identical, and their pharmacology may actually be different. We can really see the first example is that maybe right in your mind is L versus D amino acids. One works in our body, one doesn't. We'll talk about the amino acids just a little bit and when we finish this chirality idea. But what's really tricky about this chapter is being able to visualize the mirror images of the molecules and being able to manipulate them in a 3D space, because we are dealing chirality specifically with sp3 hybridized centers. That is the tetrahedral. Now, for the history. Chirality was identified in the mid-1800s. Louis Pasteur, I'm sure a lot of you have heard of pasteurization. Louis Pasteur was born in 1822, and I really, really love him as an example of a brilliant chemist. He really wanted to be an artist, and his parents told him no. And so he decided to choose science. There was a really awesome article written about the artistic side of Louis Pasteur a couple years ago. And I will definitely be sharing it with you after our discussion of this. I always share it, and I think it's really amazing, where it simply says he settled for science. But what he did was he bridged this unique ability of him to artistically see the world in science. At 24 years old, he discovered chirality. Now, chirality was understood to a point. There wasn't the name of chirality. The name chirality comes from chiral, the Greek for handedness. So I want you to just look at your hands right now. Stick your hands out in front of your face. Do you see a mirror image? Doesn't matter if you're looking at the front, the tops of your hands, or the palms of your hands. You can look at your hands as chiral objects. There is a non-superimposable mirror image. You can never put one hand on top of the other and have it perfectly match up, right? It's either palms to palms or tops to tops, or a palm to a top and the fingers don't match up. Though that is the perfect definition of a chiral molecule or a chiral object. And so this idea was understood to a point because we knew that one unique property of a chiral center was optical activity. We will talk about optical activity in sections 4. Let's look at the actual molecule here on the right-hand side. Notice the carbon in the middle. I'm just going to put a blue dot. And I'm going to label just the same as I did before. 1, 2, 3, 4. I'm not labeling to name. I'm not labeling to prioritize. I'm just numbering that these are 4 different groups. We have an OH, we have an H, we have a methyl, and we have an ethyl. Those are all 4 different groups. Now this molecule is chiral, and these are 2 different molecules. They are stereoisomers. If you try to build this in your molecule kit, you will notice, just like your hands, they are non-superimposable. There's no way to line them up and actually overlay all 4 groups identical onto each other. They're perfect mirror images. When you can classify a compound as having a chiral center, at least one chiral center, when you draw the mirror image, that is a different molecule. There are 2 mirror image molecules that are non-superimposable. They are not identical. They have a special relationship. They're called enantiomers. So how do we draw it? The first way, very, very easy. Here's your molecule, one molecule. And we want to draw the mirror image in this box. Now let's imagine that this is a mirror. You can practice this in your own home, right? We're going to start by drawing the exact thing that we see. Start here. Put it on the opposite side. That carbon is this carbon. Notice I'm just drawing the mirror image. I still have my wedged chlorine, and I still have, let's put a little plus sign. right there, just to start identifying how we can draw that mirror image. The best way is to simply draw the opposite of what you see, right? But see, notice the chlorine is still on the wedge, right? This would be a pair of enantiomers. Enantiomers right there. Different molecules, not identical, different properties, but mirror images, non-superimposable. Another and often easier way to draw the enantiomer of a chiral center is to just invert. What was wedged, make it dashed. What was dashed, make it wedged. So these two are enantiomers. We just flip what was wedged to dashed. These two, methamphetamine, enantiomers. This molecule on the right-hand side, the methyl group right next to that amine group, methamphetamine, one is very active and illegal to consume into your body. The other one does nothing and is not illegal because it does nothing into your body. All right, so we've identified we had a chiral center. We can draw the enantiomer. Right? We can draw the mirror image either by flipping the wedge and the dash or by drawing the actual mirror images, similar to how our hands look. But what does that mean? How do we designate a different name? Because if it's a different molecule, it needs a different name. So we have a different way of doing that in the naming. Enantiomers must have that different name. So in 1956, the Kahn-Ingold Prelog system, CIP, was developed by 3 scientists who knew that the chirality needed to be incorporated into the name specifically for the pharmaceutical industry. So this R or S denotion is part of the procedure for the Kahn-Ingold Prelog system, often abbreviated CIP. In atomic numbers, let's go ahead and just write out a molecule. And I'm going to put in the hydrogen. We're looking at one chiral center here. A little dot. That's the chiral center that we want to look at. Okay, so using atomic numbers, we're going to prioritize the 4 groups attached to the chiral center. The higher the atomic number, the higher the priority. So out of all of these, the atom that has the highest atomic number is chlorine. Chlorine is given priority group 1. The other things directly attached to this guy is a carbon, an oxygen, and a hydrogen. I'm going to put a little eraser mark right here and actually put the carbon so that we can see those were the choices for the first atoms directly connected to the chiral center in question. We had carbon, oxygen, chlorine, and hydrogen. So chlorine with atomic number of 17 comes first, then oxygen with the atomic number of 8, then carbon, and hydrogen will always be the lowest priority group when it's there attached to that carbon chiral center. Hydrogen just happens to have the lowest atomic number. So when we're looking at this, we've numbered it. Excellent. Chlorine's number 1, then oxygen, then carbon, then hydrogen. Now we can move on to step number 2. Step number 2 is to arrange that molecule in such a way, and I'm going to give us room over here. Arrange that molecule in such a way that the 4th priority group is in the back. So let's just get this guy on the paper. And what I want us to think about here is really trying to understand how we can rotate. There are a couple of tips and tricks, but really the best thing to do is to take that group right here along that plane and literally just rotate and to twist so that when we actually can visualize what happens, we see that we're really just pivoting that hydrogen to the back. So think about a pancake flip here, right? Think about you're flipping a pancake. You're not changing anything about that pancake. You're just seeing it from the other side. So I'm going to go here and draw that carbon backbone differently. And hopefully we see this flip as it occurs, as a pancake flip. Everything gets flipped. Everything's opposite, right? These are identical. I just did a flip, right? So one way that you can start to think about this is draw this molecule on a piece of paper and be able to kind of visualize what's wedged and dashed and literally try to flip it over and redraw it on the back side of that paper. Now, this is just one way to start rotating things in three-dimensional space. Do what's best for you, but now what we can see with our priority groups is that 4 is in the back, right? 4 is in the back. So we have successfully flipped that 4th group. Excellent. Now, here's our molecule, right? We want to be able to say, do we have R or S? So let's count. We'll start at 1, and we'll go to 2, 3. Remember, we ignore 4. This is counterclockwise, right? Now, I know a lot of you are probably thinking like, oh, how am I going to remember? Counterclockwise is S, clockwise is R. Take a moment, start to draw your S. Which way are you going in that circle? Counterclockwise. What? You won't see this in a textbook. This is something that Lauren just came up with on her own when she decided to be defiant and not memorize stuff in Ochem when she took it the first time many, many years ago. Dinosaurs roamed the earth then. Notice that starting of the S is counterclockwise. So if you do that 1, 2, 3 rotation and you go counterclockwise, that's S. Here's the magic trick. Start to draw your R. What? Counterclockwise in that circle. There's your R. So clockwise is R, counterclockwise is S. We have, in this specific molecule, the S enantiomer. So we can look at this guy and say, okay, there was the S. How can I draw the R? Well, I can draw the mirror image, or I can flip 2 groups. Let's do that one. H flips with Cl. Flipping any 2 groups works. To make the enantiomer, what I want you to hone in on here is that by flipping any two groups, wedge and dash is, I think, the easiest. Those are usually smallest groups when you put small things on the wedge and the dash. In Ochem, not a carbon backbone gets flipped, but just substituents. But flipping any 2 groups makes the enantiomer. So this one is the S center, and this one has to be the R center. Excellent. Now,